Okay, hey. Feels like it's been a little while. Um, Now we're going to get back into it. And we're going to start talking about how to start manipulating objects, uh, not just with these sort of vectors, but with forces. And it's kind of funny to say, well, what's the difference between a vector and a force? And the answer is there is none. But the idea of a force is effectively taken from physics, which we'll talk about a little bit here. In that a force is a vector of a force, which is applied to an object. But to apply a force to an object, you need to start thinking about the mass of the object and the actual physics of the object. Whereas before, we were simply dealing in displacement, where you had a position, which was a vector, it was a point in space. You had a velocity, which again is a vector. It's a, time over distance over time, a rate of change of the position. And then you had an acceleration, which was a rate of change of the velocity, or the change in time over the change in distance over time squared. So the answer to how to actually get these values, like how do you figure out what an acceleration is, what a velocity is, and as a result what the position is, all of that comes out of physics, of forces actually. And I think that if you have some experience and background in physics, like if you took it in high school, a lot of these ideas will be pretty familiar. And we'll talk about how to apply them in a game engine, in an interactive experience, and how to model them in an interesting way. And this will flow into later lectures of how to make objects interact and behave in interesting ways. So cool, let's jump into it. So what we're going to talk about, this is actually a new unit, and we're going to talk about how to create these objects, how to move those objects with vectors. That should be kind of a review. Sorry, we've already talked about how to do this. We've to create objects, to make those things move with vectors, and to move them with the keyboard input. And now what we're going to learn is how to apply forces to those objects, things like wind, things like gravity, love and hate, which are also forces in a way, and then also how to apply forces to things with different masses. One thing for those of you guys who have done physics, we will not be talking about, as far as I know, rotational momentum, rotation inertia, and that kind of stuff. So we're going to stick to effectively particle level physics, or particle forces, which means that an object is treated as if it's a particle with no rotation orientation, even though you might have orientation obviously in your game. So for those of you that don't know what that means, don't worry about it. But for those of you who do know physics, keep in mind we're not going to be dealing with actual angular forces. So cool. And in the next lectures after this unit, we're going to start to talk about how to make objects behave, how to make them react. And so if you played a video game, you probably know that objects don't just sort of bounce around randomly. They have some kind of order. They tend to follow a kind of pattern, usually in order to progress the point of the game. And that's something that we're going to add in the next unit. So let's treat acceleration as a vector, which we've already been doing in theory, but let's talk about it a little bit more deeply. So right now, this is our formula for movement. We take our direction, we normalize it if it's not already normalized, our orientation, so to speak. We multiply that direction by our acceleration rate, or our speed, and then we get our acceleration vector. And then we add that acceleration to our velocity. If we're slowing down, then we do the same thing, except we do it in the opposite direction. For example, if we have a friction equation, we apply that to we apply a coefficient of friction in the opposite direction of our velocity. We limit our maximum velocity to a particular speed, which you'll find once we go into physics, it becomes a lot harder to kind of arbitrarily grow your velocity. Well, that's not really true, because acceleration will just apply to velocity in the same way. So I guess We're not talking about theory of relativity here. But generally speaking, when you ground it in the mass of an object, things won't just go like fly off into space as easily. You still can obviously make that happen, but there's a little bit more control. And then, so going back to what we're doing today, right? We limit the maximum velocity to some speed, kind of clamp it, and then we add the current velocity to the object's position, which gives us over a delta time step, and then we draw that new position. That's our current movement. So let's kind of talk a little bit about this a bit better, like in visually, right? We've got our direction vector, we normalize it, we multiply that by acceleration rate, we add the acceleration to the velocity. If we're decelerating, we are doing it the opposite direction. We clamp the maximum speed, and then we add the current velocity to the object's position. So if you're here, you're moving in this direction, you move that direction. Cool. Right. So when we rotate the direction vector, now we are pointing in a different direction. Now we may be moving and then pointing in a different way than we're moving, right? And so in that way, we are now adding an acceleration in a different direction than the current velocity. So again, this sort of shows how you can rotate an object or move it in a different direction. So let's talk a little bit about the relationship between velocity and direction. So we're using already a direction vector in our code. Right, the magnitude is set to 1, and this is effectively pointing, when we have as 1, 0, 0, this is effectively pointing towards 0 degrees. We can change the direction blatantly to point to any particular angle using a key press, right? So we go left, it rotates, go right, it rotates, right, around the unit circle. So obviously 0 degrees, 0 degrees, 90 degrees, and so on. But since the rotation is the only thing that's changing, right, its magnitude's not changed. It's still normalized during the rotation. So we don't need to normalize it yet. That's not the only way to use a direction vector. Sometimes objects can change direction without actively choosing to. For example, with a force being applied to them. We'll get into that. So how do we deal with that? How do we apply forces to change an object's direction without us explicitly setting the direction of the vector? How would we go about that? What is that relationship between the direction of an object and its velocity? So let's go back to our code as it is. If your code doesn't look like this, that's okay. This is just sort of, my code doesn't look like this either, but it's fine. We have a position, a direction, a velocity, and acceleration. These are all vectors. Right? The direction right now is the only thing that's set to a particular direction, a particular value, which is pointing to the right in x. And then we have our acceleration rate, our maximum speed, our total rotation, and our angle delta. Right. And now when we start, we set these values again. It's kind of redundant. Well, I guess in the top it's a comment. So in start, we set them. You can obviously set these via inspector, or you can also initialize them above if you change everything. And now in our update function, we have 4 things we have to do. We apply the rotation to the ship, to our vehicle. We update its position based on the velocity. And then we wrap the ship, so if it moved beyond the screen bounds, we push it back to where it's supposed to be. And then we set its transformation so that we can see it where it should be. So basically what we're saying by set transformation, by the way, just to be a bit more clear about that, is we are updating the object's information, meaning in Unity or in your engine, to the internal state that you're setting in here. So you're setting position to the actual position of the object, so you're converting it, because we're not operating, these values are not being operated directly on the Unity entity. Cool, so let's talk about the turning ship, right? If we have a left arrow or a right arrow, we apply, we kind of create a quaternion based on our angle delta, which was our internal kind of like counter, how much around we're going. So this is one way to do it, versus deflecting an existing thing. We're just creating a new one based on a rotation angle. And when we do in the opposite direction, we do the opposite thing. Yes, that's correct. Cool. And again, now we're updating position. If we're moving forward, then we calculate the acceleration in that particular frame, right? And we add to the velocity that acceleration. And when we clamp the magnitude, because that's safe to do it there. You could do it outside of this loop if you want, outside of the conditional if you want, but since we're only changing velocity here, it's okay to do, or at least we're changing it in the positive only here. If we're not accelerating, then we can decelerate based on friction, right? We're just multiplying our velocity by itself, but reducing it by 5% or by some kind of coefficient. And then we clamp its magnitude to 0 when it's sort of past a particular epsilon. So you can imagine, right, if you're 95% of 0.000001 is like 0.000095. So it's kind of annoying. It'll eventually, you want to kind of taper it off. So once you're beyond the particular epsilon, just set it to 0. And then at the end, finally, we apply our new x plus the velocity. Our new position is going to be equal to our an addition of our velocity plus the change in time. So pretty standard stuff. Yes, cool. This, the only difference here is if we want, right here, where we're doing this based on vector movement, like we're using the delta time. If we do it this way, if we take the delta time out of the equation, we're now doing it based on a per frame basis. I'm not entirely certain why this is important to note, because you always want to have a delta time in there because all of these values are based on time. But you could, in theory, do this per frame. It's just you have to ensure your frame rate is consistent. Most games aim for like a 60 frame per second or 30 frames per second, so sometimes that's safe. You can actually just do it inherently that way, but and oftentimes it doesn't actually matter. Like, games don't have to be physically correct either, so you see this a lot actually, and it's not a big deal, but it's best practice to use the delta time. So let's just remove it, I think, to just make it simple, so we don't have to worry about the time for a minute. And you can kind of see here right now, we only have one force that is really being applied to the vehicle. Right now, that's what's moving us forward. And by forward, I mean in our directions, right? So we would take our direction, which is a unit vector in the direction that we're facing, times the acceleration. So we're scaling it, right? And that becomes your acceleration vector, which is applied momentarily to the velocity. Now I say momentarily because it only happens when it registers to the up arrow. So I know that sounds kind of like, well, what if I'm holding it down? And in that case, you're applying it momentarily many times, like every single frame. But you really do have to kind of keep that concept in your head. These things are not continuous. These happen in these sort of time frames, right? And in each time frame, you're applying what's called an impulse, actually, and we'll talk about that a little bit more later, because it's really critical you understand that these things are treated as impulses, as momentary or infinitesimal sort of forces that are applied each frame. If you had to do this, for example, without impulses, you somehow could apply a continuous force throughout a period of time. You would have to do sort of the calculus to integrate that. But impulses give us a nice simple way where you think about, well, all the force applied in the last time frame, I'm sort of accumulating it into this one impulse. So I'm treating, say, 100 milliseconds of force into 10 sort of snapshots, or I'm sampling it. I'm getting into a little bit of depth here, so I don't recommend thinking about this too much, but just keep in mind, this is where we're applying the force momentarily. Finally, We are now wrapping the ship into this. If you guys did the assignment, you know it's not this simple. You do have to calculate the position of the screen, the size of the screen. You can't just do it with 10 and 5 and whatever. But the idea of wrapping here is pretty simple, right? If you pass a particular, this point here, you set the position here. And again, this is a bit of a simplistic thing, a simplistic function, because you also know you probably want to calculate the bounds of your object, so that when you're just barely touching this, maybe you're poking out here, and you might have to create sort of a dual object where you have one here and one here, and now you're getting a bit fancy. But that's the way, if you really want to do a perfect wrap, you have to calculate the size of your object, the orientation of it, and sometimes create two of them when they're on the edge. And then finally, the set transform function, as I was mentioning, we now actually have to set the transformation of our entity, of our prefab, to the position, our internal position, and our internal rotation. So that's what we're doing up until now. Hopefully we're on the same page. Now let's talk about how do we do a lot of that stuff with forces. So what is a force? And the original version of these slides have a lot of like wrestling. I'm not a big fan of wrestling or any kind of like, that, or any kind of distracting slides. So I changed a few things. So if you're comparing this to some of the other slides, it might look a little bit different. I made a few changes here and there. For the most part, it's the same content. So if you're talking to some of your friends in different sections and they're like, yeah, did you see the wrestling stuff in the slides? And you're just like, no, we had a bunch of weird blobs and things. That's why. So anyways, okay, what is a force? And we're going to talk about this from the perspective of code, not physics. So for the physics fans out there, please don't, please don't attack me on what I say differently than the physics of it. But I did try to root this a little bit more in physics than previously in these slides. So ultimately, a force is a vector that causes an object with mass to accelerate. Now this is actually kind of a philosophical concept, because the concept of mass actually came out of force, or the realization, this was Newton's stuff, right? The realization that objects react to these forces, and that the mass, that different objects with different masses react to forces in different ways. In fact, the mass is defined by way of how an object responds to an impulse of force. So you start to get into sort of like, well, what came first, the chicken or the egg, the force or the mass? And the fact is they're the same concept. Mass and force are the same thing. I like to think of force actually as a body's willingness to move in reaction to a force, right? And that reaction, that willingness to move, is acceleration. So this is a good time to talk about, the third law, but let's go into the first law. So the first law that Newton noticed, and I'm kind of hiding this. So an object at rest stays at rest, an object in motion stays in motion, at a constant speed, direction unless acted upon by an unbalanced force. Okay, so in short, if you take an apple and you throw it, it'll keep going unless a force is acting on it to slow it down. So if you're like, hey, Don, I took an apple and I threw it at my mom and it didn't keep going because it bounced off her. Well, your mom, when you threw the apple, applied a force on that apple that made it bounce off. Then you're like, well, Don, I took it out to a field and I threw the apple in the field and it didn't keep going, didn't go in outer space, it came down and landed in the field. And I'm like, well, there's this other force that keeps us on the ground called gravity that brought it back down. Now these are all things that probably make sense to you if you've ever been alive at any point and interacted with anything in your surroundings. Objects behave the way we do. But it's actually funny how foundational this realization was, because before Newton thought about objects, staying at rest or moving on only in reaction to velocity, people were like, I think it was, I forgot who it was, but the existing, I think it was like Socrates maybe, I forget, but the existing mentality was that objects uh, maintained a velocity because of a consistent force being applied to them. And this makes sense because if you think about being in medieval whatever or in the Roman times, you didn't have the concept, like nobody saw what ice was that much. Maybe people up in the north knew about forces and this kind of concept. But generally speaking, if you had a wagon and you were pushing on the wagon would keep moving at almost like a terminal velocity while you were pushing on it. When you let go, it stopped moving. So you're like, oh, well, things move because I push on them. And so that was the existing thought at the time. You can kind of imagine being a human being up until Newton's time. It was very difficult to realize that, wait, actually, no, objects react due to forces. And it was a pretty revolutionary thing to think, well, actually, that cart stops moving not because we stopped pushing, but because there are other things pushing on it in the opposite direction that we're not aware of, like friction, for example. So now we know this is true to a certain degree without talking about other things that are not true about it. But for the most part, if we have an object and we apply a velocity or we apply an acceleration to it, it receives a velocity, it maintains that velocity until it loses that velocity based on another acceleration in an opposite direction due to a different force. So if we have we start at velocity 0, we don't do anything, the velocity stays 0. If we have a velocity of 1 and 2, 1x and 2 and y, and if we don't add any forces, then it will continue at that velocity forever. So here is the third law. We're kind of skipping the second law because the second law involves a bit of math that we're going to talk about. But this one is actually really profound and kind of fits into that, like, well, why did that cart stop moving? The cart stops moving because when I push on it, and I let go, well, sorry, why does the cart hit this terminal velocity? Why, when I push on it, eventually I can push on it only so hard, and it will only go so fast, right? Why is that? What is causing it? And that's because the friction at a certain point equals the force, my force that I'm applying, plus the, so the accelerations imparted to the two are equal, meaning the velocity gets maintained, right? So by pushing at a certain speed, I'm overcoming the acceleration due to friction, but I'm not, so the velocity stays maintained, right? So if you think about pushing a cart, actually, this is not usually the image you think about with the third law. You don't think about a person pushing a cart, but I like that image a lot better than even, this is the Newton's cradle, which I'm sure you've all seen. But let's talk about the cart idea. Right? A cart, or terminal velocity, if you think about it even in the concept of jumping out of a plane, at a certain point you jump out of a plane and the friction, the air drag pushing you up is equal to the acceleration, the force of gravity, and so you hit a particular speed, right? And if you want to see a really good example of this, skydivers use it to great effect to be able to sort of, do these tricks and things where they change their surface area to create more or less drag so they can go up and down respective to other people in their area so they can do synchronized stuff. But the classic example is Newton's cradle, right, where you have these balls, they're equal mass, which we'll talk about in a second. They're perfectly aligned so that when one hits, it hits it in the same direction that all the others hit. It's like a line, a parallel line. And you take one ball and you drop it, and the other balls seem to not move, and then the last ball pops off and does it again, and it does it forever. And what you don't see is the forces being effectively transferred from one ball to the other, to the last one. And the last one doesn't have one to bounce off of, so it goes off, and then it comes back, and then the same thing happens. So a really cool toy that I'm sure many of you have seen, and if you haven't, go get one. They're like $5. So to be a bit physically accurate, if we apply a force to an object, the object will apply a force in the opposite direction to that object. Now, this is a kind of not always true like it is. It's always true, right? When you have a force in one action, you have a force in the opposite action, in the opposite direction. But keep in mind that the two objects. So okay, sorry. This is always true. It's always like a negative force. But keep in mind, and we'll talk about this in just a minute with the second law. Object A and object B may feel the forces in a different way. And so what you'll see is that sometimes you'll have a situation where you're like, here's a big object and here's a small object, and the big object comes and hits the small object and imparts on it a force of some kind, right? And in that moment, the small object imparts on the other object a force of some kind, but yet this object barely slows down and this object will fly off, like at a ridiculous speed. And I think that comes into play in terms of understanding, well, momentum and how forces interplay into momentum, but we're not going to talk about much of that in this lecture. So keep in mind the forces are equal in that scenario, but one object is small, so it feels the force significantly more than the big object, which barely feels it. So yeah, it's not always necessary to code up these laws, by the way. Like, for example, we talked about friction or wind. Wind force is a complicated force, right? Like actually calculating the fluid dynamics of air and how it interacts with your object, that's like not simple, right? But we can approximate it as a drag, as we've seen before. If I apply a force or a force in the opposite direction of my velocity, that is just my velocity times -1 times some coefficient, that is sufficient to model wind drag if you don't want to go into the particulars of what actually is going on. So, okay, this is the fun one, that Newton's second law is really that underpins that idea that objects respond to force based on their mass. That the way that the force is measured actually is by taking a mass, applying to it an acceleration of some kind, and then you can measure the force because based on the acceleration of a mass, how it responds to that acceleration is going to be different for different masses, right? A bigger mass will respond to the same acceleration. It requires a much higher force to do that. And sometimes F equals ma, like this is a fundamental identity of the Newton's laws, sure, but it's not, and it's always like represented this way, like force equals mass times acceleration, but you hardly ever use it in this form. Much more often you're interested in the acceleration due to a force, right? Like, you know, like with gravity, we know the acceleration due to gravity. So great. It's an easy thing to do. And so often we learn this particular equation in this form, because then we know that the force being applied to me is my mass times that acceleration. The force being applied to you is your mass times your acceleration. And you're like, wow, like that's cool. Like our mass isn't really important in regards to the acceleration that we feel compared to gravity. Now, that's not entirely correct. There are small, minute changes between the force I feel and the force that you feel. But they're so small that we can approximate the acceleration due to gravity as the same constant for most objects that we would ever come across. Everything from like an ant to a human being to a Boeing 747, and in some cases even like things like the moon. But when we talk about the moon, for example, the moon starts to apply a force on the Earth as well. So if you're familiar with the equation for gravity and the force due to gravity, right, you know that the masses of both objects do play in there. But because the mass of the Earth is so huge, the force that I feel due to the Earth largely is like my weight does not matter. My mass does not matter. So, but more often than not, you will be using how do I calculate the acceleration from a force? And the way you do that is you just take that m and you put it on the other side of the equation. So acceleration is equal to force divided by mass. And that form, the acceleration equals the force divided by the mass, is a little bit more of an intuitive way to think about mass and force, because now you can see the heavier something is, the less it's going to respond to force. And it's sort of its willingness to move in response to a force. This top diagram here shows the way you would measure force, because we know, like I was talking about the gravity, we know the weight, the mass of an object compared to the mass of the Earth. We know the mass of the Earth relatively well. Not that it even matters. We just know that it's so much bigger than your object's mass that we can create a measurement of what's called newtons, right? So you have a spring, and the spring applies a force in one direction, which is actually equal to its coefficient of whatever, the K coefficient, I forget what it's called, times its displacement, right? And that's going to be equal to the mass times the acceleration of the gravity. So you can actually use this little spring attached to an object to measure relatively accurately the force being applied to an object. So in that sense, it's accurate to the point of how approximate how much the mass of your object is applying its mass to. Anyways, I'm going too deep in this stuff. If you know physics, I'm sure you know a lot of this stuff already. And if you want to know more, please bring it up in office hours. Cool. So we already kind of talked about this. When you have a small mass, it's a much smaller acceleration required to move it versus a bigger mass. So again, talking a little bit about this and a bit further, right on the right, you can kind of imagine a bunch of objects that have let's immediately talk about this. All of these objects have the same density, meaning they're made of the same stuff. Okay, it doesn't matter what stuff they're made of, but it's all the same. And so you can kind of see if they're bigger, they have a bigger mass. If they're smaller, they have a smaller mass. Now you know this is not always true. If an object is bigger, it doesn't mean it's heavier than a smaller object, because it's based on the density of the objects. But in this case, for this example, you can see how big objects move slower in the presence of the same force. Or when a bigger object hits a big object, that object moves slower than if a big object hits a small object. And you can kind of see in this particular image all the various permutations. For example, in the top one, we can see a big one hitting a bunch of big ones, and they move in a particular speed. But if you compare that to the middle one, where the big ball is hitting two small balls, you can see how both those balls move, and the ball on the right, the small ball on the right, is moving faster, perceivably, than the one on the top. So this is a nice little kind of explanation and demonstration of this stuff. So again, this is really important to note. Objects' mass is not related to their size respective to other objects. So like if you've got a bar of gold and a bar of the same size of plastic, you know which one's going to be heavier, which one's going to have more mass. So the actual mass of an object is dependent of its constitution, of its material, not its size. Obviously size affects it, right? A bigger piece of gold and a smaller piece of gold are going to be different weights or different masses. But just keep in mind that the mass can differ across objects. In a game, this is really important, because you can have a rock and like a pillow, and you want to make one move really rapidly and the other one moves very slowly. And again, to note, and we've talked about this at length already, the acceleration due to gravity is not going to be related to the object's mass. But the force it feels, obviously, is going to be related. So if you have an object that you throw up in the air with a velocity, and it comes back down, it's going to have a particular force related to its mass, depending on if it hits something. So this is important if you want to like make a projectile that hits other things, for example. So again, mass is your object's kind of willingness to move based on a force. The harder you push, the faster you'll move. The bigger you are, the slower you'll move. I mean, these kind of relationships all come out of these set of equations. So you can treat mass as like again by the size. Bigger objects of the same stuff are more heavy. You can represent it as textures and sound effects. Really, like how do you treat an object in a video game as massive is something that's up to you in terms of how do you represent it. Like we talked about, for example, with textures, you can show it being heavy by way of like, oh, this is a metal or stone versus this is wood or straw, right? You can do that with textures. Sound effects are also very effective at kind of representing or showing that something's massive. Because if something hits another thing and it's soft, you kind of hear a little dull, like a boop, kind of sound. But if something's heavy and large and massive, and it lands, and you can make a kind of like a big poof, sort of explosion sound, like an explosive sounding effect. So we'll talk about how you accumulate forces, but multiple forces can apply on an object simultaneously. In fact, they hardly ever don't. An object generally, unless you're in outer space, has many different forces being applied on it. And acceleration is the sum of all these forces. So that is kind of a piece that you might not see, right? The acceleration isn't just you're adding each force imparts onto the object an acceleration vector, and your actual acceleration to get the final acceleration, you just add those all together, and you'll get one vector. So you don't have to kind of do all that multiple times. The mass will affect the movement of the object. And then you can also create new forces. In theory, you don't have to follow the laws of physics in games. This is where you can use these same laws, right, and make like a love field. I don't know, like like there's an object and you in a game and it's attractive. You love it. Your character gets pulled into its gravity well, into its love well, so to speak. So you can do a lot of fun things with this stuff and make the game interesting in that way. So let's talk a little bit about multiple forces on a single object. So this is a free body diagram. If you're familiar with that, I'll talk a little bit about this in a minute. You probably won't be dealing with this kind of free body diagram in that you're probably not doing something innately physical in a project anytime, like in this particular project. But here we can see an object that's laying on an inclined plane, on an inclined surface. So, and we assume that let's assume that it's at rest, right, in this particular image. Meaning, if we looked at it, took away everything, and hit play, the object would stay where it is. And so you're like, well, how does it stay where it is? I see a normal force, and the normal force, by the way, is a direct corollary from the Newton's third law, which is where you see a force, there's an opposite and equal force in the opposite direction. And the normal force, we're looking at this object, we can intuitively see that the normal force, the object is staying still, but we have gravity pulling it down. So if you took gravity and you projected it onto the perpendicular of the plane that it's sitting on, you would know, well, there's a force pulling it like into the surface, right? Because it's trying to go down. But that means that surface is applying an equal and opposite force onto the object in the opposite direction. And then you're like, well, what about the other part of gravity? Clearly gravity is pointing down, right? So if we projected it this way, there's another piece that's pushing it down the plane. Or we've all seen objects fall down an incline, right? Or objects roll down an incline. So now you've got another force that's being applied in the opposite direction. So let's take a quick look at that, right? If we took the weight of gravity and we now separated it into its equivalent parts that are, one is parallel to the normal force and one is perpendicular to the normal force or parallel to our incline, we can see that we have two forces where Wn, which is normal, is going to be equal to the opposite of the normal. Actually, it should be negative absolute n. I mean, it doesn't really matter, but it's just a value. In this case, Wn is a value. It's the component of W that is pointing in that direction, right? And so you can kind of figure out, okay, well here, this object is actually has, you know, 3 forces being applied to it. The force of gravity, then you've got the force that's pushing it out of the incline, and then you've also got a force kind of like pulling it down the incline, which is the portion of gravity that is pulling us down the incline, which is parallel to the incline. But then you've got a force of friction, because the object's trying to move, but there's a force of friction, right, where the 2 objects meet. They're, you know, creating friction against one another, and so that's inhibiting the movement down the plane. And so if you took all of these forces and summed them together, right, N plus F plus W, what you should see is 0, if you're looking at it and it's not moving. Now, if it is moving, how would you calculate the force? How would you calculate its movement down the plane? The way you would do that is you would sum them all together, right? And then you would see, okay, well, Wn and N are equivalent. They cancel each other out. So let's throw that away for now. That's an easy way to do it. This is kind of a simplification. And then the final force is simply going to be the force of friction minus Wp. And I didn't quite sufficiently spec this out, because Wp in here is a constant, right? It's just going to be the magnitude of W times the sine of theta of that angle to get that component that's parallel to the plane. What we want to do here is then, you know, we can actually get that component pretty easily by adding the normal force to the gravity force. But usually you don't have the normal force, you have to calculate it yourself. Either way, we can see that final W plus the weight of the force of gravity plus the normal force pushing it out, that's going to be Wp, and if we subtract friction from that, we'll see what the final force is. And what's cool about this is friction is complicated. It's not ever going to exceed, our final should never exceed this friction force. The sum will either, the combination of the two will either be 0 or some amount pushing down. So you might be kind of slowly sliding down. Or if this incline is made out of ice, maybe your friction's very low and your final is actually quite fast. But there's always some kind of friction pushing you in the other direction. But you can kind of see in a relatively more complicated scenario, we're just summing these. These are all just vectors. Okay, so I'm going to stop here because now we're going to go into sort of a different portion of this project, of this lecture, where I'm going to pull up a project and kind of create some forces applied to objects and run through that. So that'll be a separate lecture to this one. All right, see you in a minute.